Hello, my name is Robert Smith, and I'm with New River Community College, and today we're looking at balancing nuclear equations. I have a couple of examples that we'll work through today, but these are relatively simple examples, and so please be aware that the examples that you might experience on a test or on homework might be either more advanced or they might be in the form of a word problem, like asking write the balanced equation for the alpha decay of uranium-238 when it emits one alpha particle, or two alpha particles, or 10 alpha particles. It's just a matter of how the question is asked, and we'll talk about that a little bit as we go. In balancing nuclear equations, in addition to using the isotopes available to you by extrapolating from the periodic table, there are a few species that we use in balancing. They include protons, neutrons, alpha particles, beta particles, and positrons. And actually, we could call beta particle is also an electron for all intents and purposes. So the number in the superscript, or the upper number, is the total number of nucleons, which means it's the sum of the protons and the neutrons in that species. The number in the subscript, or the bottom number, is the total number of protons in that species, with a little bit of an exception with the beta particle. So a proton has one proton and one nucleon, which happens to be the proton. A neutron has no protons, which is why it has a 0 at the bottom, but it has one nucleon, and that happens to be a neutron. That's why it has a 1 at the top. An alpha particle is essentially like a helium nucleus. It has two protons and two neutrons, which is why it has a 2 at the bottom and 4 at the top. A beta particle is essentially, it is identical to an electron. And so that's why we sometimes call it an electron instead of a beta particle. And the difference being that electrons have their whole existence, for all intents and purposes in this class, have their whole existence outside of the nucleus. Whereas a beta particle is an electron that originates and is emitted from the nucleus. So beta particle is a little different, and we use it only in nuclear chemistry. A positron is just a beta particle of the opposite charge. So the beta particle has a -1 to denote that it's the equivalent charge of a proton, but it is a negatively charged proton. But it's a different size, and that's why we call it a beta particle. Just as why we call a positron a positron. It doesn't have any nucleons, so it has 0 at the top, but has a +1 charge. And so positron is essentially a positively charged electron that's being ejected from the nucleus. Okay. So in solving these kinds of equations here, what you would do is you would take the superscripts and set them equal to each other on the right-hand side and the left-hand side. And then you do the same thing with the subscripts. So we could say that 238 is equal to 234 plus some number. And that some number is quite obviously 4. And then 92 is equal to 90 plus some number. And that number is very obviously 2. If you subtract 90 from both sides, you get 2, y is equal to 2. So this means that our parent species, uranium-238, decays into thorium-234 plus something that has a 4 and a 2, and we can readily see that that's an alpha particle. So this is alpha decay of uranium-238, emitting one alpha particle. If it was given to you in a word problem, that's what it would ask for, or what it would say. It's write the balanced equation for your the decay of the alpha decay of uranium-238 to thorium-234, something like that. Or it might say the alpha decay of uranium-238 ejecting 1 alpha particle. That's another way of formulating that. Note that the 92 signifies uranium and the 90 signifies thorium. So you would never have something where your daughter species, in this case, would not be uranium-234 with a 90 underneath. We use the number of protons in our periodic table to identify the different elements. So it's very important that you correspond the subscript with the appropriate species. And that can get a little tricky when you're looking at protons. You might be tempted to put a hydrogen atom, or in the case of alpha particles, you might be tempted to put a helium atom. But just bear in mind that when we're dealing with these situations, you'll be told explicitly what you're looking at. And again, the only difference between a proton and a hydrogen atom is an electron, and the only difference between an alpha particle and a helium is 2 electrons. So we're not dealing with electrons, we're only dealing with nuclear material. So our next one, quite similarly, we would set to the left-hand side equal to the right-hand side. So uranium-234 is equal to protactinium-234 plus some unknown, and it's obvious that in this case that x is equal to 0. And so 90 is equal to 91 plus some y. So y has to equal -1. So coming back to our species up top, we can see that to have a superscript of 0 and a subscript of -1, this process is called beta decay. It's ejecting what is equivalent to an electron from the nucleus. So we say 234, 90 thorium is undergoing beta decay to protactinium. Another way to look at this would be to say, if they asked what balance the equation for, write the balance equation for thorium undergoing beta decay to protactinium, or thorium undergoing beta decay and emitting 1 electron or 1 beta particle. So those are equivalent. So practice these as much as you can to get a firm grasp of how to work through them, but here's a couple of very simple examples that'll get you started.